Alright, hi everyone. Today's lecture is where we're going to be continuing regards to our first stability lecture where we observe the Routh-Hurwitz criterion and how we actually form the Routh-Hurwitz table and determine the stability of the system by watching the signs of the coefficients in the first column of the table. This lecture focuses on special conditions that you may encounter when solving for different rows in the table. And each one of these conditions is going to be discussed in detail as we go along in this lecture. So if we have this example S equation here being our characteristic equation, as we saw from the last lecture that our characteristic equation will be the denominator of the transfer function and we equate this to 0, we can then file out the Routh-Hurwitz table accordingly by extracting the first two rows from this characteristic equation. As of such, this means that because it's the highest power of S here is going to be S cubed, we then take the odd powers of S and we watch the coefficients accordingly. So S cubed, the coefficient here is 1. S to the power 1 here, the coefficient here is 1 as well. And then we start on the next row with the S squared terms being the even power terms. So then we say the coefficient of S squared here is 2 and the coefficient of S to the power 0 here is 2 accordingly. When we do our calculation for the next row, we want to see that the coefficient here for the S1 row is going to end up being 0. And as a result, that means we can't continue the table because it's impossible to determine any of the other rows as well. And in such a case, this gives us three distinct cases that we need to examine as to how we proceed when we encounter certain conditions in the Routh-Hurwitz table. So, the first column, when we're watching this, no element in that first column can be 0. This is our first condition. The second condition is that the first element of that column is going to be 0 and all the remaining elements in the row are non-zero. And then the third condition is going to be where all the elements in that row will just be 0 entirely. So we already looked at condition 1 where no element in that first column can be 0. Conditions 2 and 3 is what we're going to be observing accordingly with respect to how do we proceed. So we look at condition 2 first and then we'll look at condition 3 afterwards. So for condition 2, this basically means that for the first element in the first column is 0, but all the remaining elements in that row are non-zero. What we do here in this case, if we apply it back to our S cube equation that we just now saw, is that we replace that 0 with a very small positive number known as eta. We then continue the calculation accordingly using eta as well, and then we observe the sign changes in the first column. Now because we know that eta here is a small positive number, there are no sign changes in this first column, so that means this entire system here is stable. What this also means is that on the imaginary versus real axis, or real versus imaginary axis for our pole zero plot, is that those poles in particular are going to be lying on the j omega axis. And any pole that lies exactly on the j omega axis, meaning that when S is equal to 0, means that there's going to be marginal stability for our system. Our system is not really fully stable or unstable, it is marginally stable, so to say. This being that the borderline for stability is at S equals 0 with respect to the left hand and right hand planes accordingly. For condition 3, we're going to observe a new characteristic equation here, and we're going to start filing out the rows accordingly as well. So we start here with S to the power 5 coefficient being the highest power of S in the characteristic equation. So we start with all odd powers of S and extract their coefficients. So 1, 24, and minus 25, as we can see here. And then the next highest power of S is S to the 4. meaning that we start with all the coefficients that are even powers of s. So 2, 48, and minus 50. We then do the calculation for the next row. But what we're going to observe here is that for the next row, the s cubed coefficients are going to be all 0. And as a result, that means we cannot continue the calculation throughout either, because all other coefficients here are just basically going to be 0 or infinity, and we really don't want any of those two values accordingly for our first column. So this brings us to a third condition where all those values in that row are 0. In order to solve for this, what we're going to do is that we take the row above it and we form a polynomial, an auxiliary polynomial equation. So for our example table here, because the s cubed row here is going to be zeros all throughout, we then say accordingly that we're going to be taking the coefficients here for the s4 row. Now note that when we extract these coefficients don't go in s4, s cubed, s squared, and so forth. This is s to the power 4, s squared, and s naught, because they are even power coefficients. So as such, when we extract this auxiliary polynomial equation here denoted as p of s, this 2 here means 2s to the 4, this 48 here means 48s squared, and this minus 50 here means minus 50 multiplied by s to the power 0. We equate this to 0 accordingly. We then differentiate the auxiliary polynomial, and then the coefficients we obtain from that auxiliary polynomial differentiation is what we're going to be using to fill in for that entire 0 row. So as such, when we differentiate it here, we can see that instead of this being s to the 4 here for the original equation, the differential means that we go from an even power here to an odd power here accordingly. And as of such, because we had the s cubed row, that means that we can now take these coefficients here accordingly and fill them in for this row as well. So the s cubed coefficients here will be 8 and 96 accordingly. We can then continue our calculations throughout for completing the entire table, and we can see here that basically there's only one sign change from at the s1 row to the s0 row, from positive to negative, meaning that this system here is unstable. And in fact, because there's one sign change, that means one pole lies on the right hand side of the s-plane. So if we actually do the pole 0 plot here, we can see that this pole here actually is the single pole that's going to lie on the right hand side of the s-plane, represented by that single sign change we saw in the first column. And these here are the roots for that s equation that we just observed. Now there are two conditions that are not stated on the slides that you need to observe in particular. One is that whenever you encounter multiple instances of when either one of these conditions occur, you just perform the same rule accordingly as well. So for instance, if you have a first row that you encounter that are all zeros, you take the auxiliary equation and you continue the table. But then you encounter a next row that's going to be all zeros, you just take the auxiliary equation for that row above and you differentiate it and you continue as you keep on going. The second thing that we need to pay attention to is that if only the element in the first column is 0 and all other elements are non-zero, we just replace that with some small positive like eta. But let's say if we continue going along and then we encounter a next 0 condition for that first column and everything else is non-zero, we just replace that with like something we refer to as like eta 2 or eta 3 as well. So we just continue it as we keep on going along. So this example here is something that we observed in our last lecture where we had the exam question, and now we're introduced to the idea of a constant that will give us a range of values for where our system can be stable. So if we fill out this Routh-Hurwitz table accordingly, we can see that it will result in this table here as well. And then because for stability, all the coefficients in the first column here need to be positive. So as of such, we're going to need to watch when 8 minus k divided by 2 is more than 0, and k must be more than 0 as well. So if we solve for the 8 minus k divided by 2 being more than 0, we can see that we end up with k being less than 8. And then watching row 4 here, k needs to be more than 0. if we combine these two inequalities, we can see that 0 needs to be less than k, which is less than 8. The reason why we say for this instance is that it needs to be more than 0 is because we're looking for full stability. We're not saying more than and equal to 0 because marginal stability is not considered to be full stability. So for absolute stability, this range here will hold true. So now that you have actually seen an example of how we actually solve for the range of k, we go back to the exam question that we saw in our previous lecture. And for your homework, I'd like for you to attempt this exam question and see if you can find out what the range of values of k are for which the system is going to be unstable. I think in the previous lecture, we also showed you that how it was possible for us to calculate the closed loop transfer function, but this was also given when we were doing the block diagram simplification notes as well in some lectures a few weeks past. So recapping, what we observed in today's lecture was the special conditions of the Routh-Hurwitz criterion, in particular when an element, the first element in a row is going to be 0 and all the other elements are going to be non-zero, and when all the elements in that row are going to be 0 accordingly. And we saw that for each one of those there were two different conditions that we need to pay attention to as we keep on going. If the condition repeats itself in the Routh-Hurwitz table, we just repeat the same conditions as well, where we do the substitutions or we do the auxiliary polynomial equation accordingly, and we continue until we hit to the end of the table. Alright, so please make sure that you attempt this problem, and I'll be doing the solution in class soon. That's it for today. Goodbye.